about radioisotopes, I'm not going to speak about radioisotopes first, but then we will start with a very basic concept called as atoms. So we will start with a very basic concept called as atoms. We will be speaking about atoms in detail, and after that we will go on to the other basics. So students who haven't learned chemistry might be having an idea, but not that much. So we'll be starting from the basics. So atoms, if you take atoms, atoms are considered to be the very smallest. Atoms are considered to be the very smallest component of an element. So this is a very basic definition of atoms. So atoms are considered as the very smallest components of an element. Element in the sense, I hope what I mean from elements here, say for example hydrogen, radium, sodium, potassium, all these things are good examples of elements. So if you take any elements, atoms are considered to be the smallest component of an element. Okay. Now, if you take the structure of atoms, let me just simply draw the rough diagram of atoms. Okay, now this is the structure of an atom. If you take this atom, you have a nucleus in the center. This nucleus is going to contain protons and neutrons. So if you take the nucleus of an atom, the nucleus of an atom is going to contain protons and neutrons. And if you take outside the nucleus, around the atom, we have electrons. Okay, so this is the basic structure of atoms. This is how an atom looks like. So if you take the center part is going to contain the nucleus, where we have protons and neutrons. We also have electrons which are present outside the nucleus, where we have electrons which are present here, there and there. Around the nucleus we have electrons. Now, another important basic information which I want to tell you is, these protons are positively charged. The protons are positively charged, whereas the neutrons doesn't have any charge, or we call it as neutral. So neutrons doesn't have any charge, that's why it is called as neutrons. And protons are called as, they are called as protons, and they are positively charged. And these electrons are negatively charged. So it is very important to understand the charge of the protons, neutrons, and electrons. So electrons are always negatively charged, protons are positively charged, and neutrons doesn't have charge. So these things you have to remember. Now, if you take an element, say for example, let me take a simplified example, that is sodium. If you take sodium, in sodium we have a term called as mass number. We have mass number. The mass number of any element, is actually the number of protons and neutrons. So you have to understand this. So we call this mass number the mass number is defined as, it actually includes the number of protons and the number of neutrons. The number of protons and neutrons altogether we call them as mass number. And the number of protons present in an element is also called as atomic number. You have to understand these basics. Okay? So, the mass number of an element is defined as the total number of protons and neutrons. The atomic number of an element is defined as the number of protons. The number of protons is the atomic number. The number of protons and neutrons is called as the mass number. And if you take an atom, we have a nucleus. The nucleus is composed of protons and neutrons. Outside the nucleus, we have electrons. So these are the very basics which you have to understand before going in with the syllabus. Okay. Now, moving on. Again, we are not again going to discuss about radioisotopes directly. We are going to start with another important term, that is isotopes. Isotopes. So that is the second basic topic which we have to discuss. Only then we will be able to understand radioisotopes. So without having an idea about atoms, about the composition of atoms, about mass number and atomic number, and isotopes, there is no point in understanding radioisotopes. That's what I am actually starting with the basics. Now, the definition of isotopes. Now, atoms of the same element with same number of protons but different number of neutrons. Okay? So, we have to understand the definition. This is a very important definition. Atoms of the same element with same number of protons but different number of neutrons. We call them as isotopes. Okay? So, we call them as isotopes. Now, so we will remember these isotopes. Okay? Now, when we are discussing about this particular topic, I want to have a small representation. That is, say for example, we have an X element. The mass number is represented at the top. The mass number is represented at the top. The proton number or atomic number is represented at the bottom. Okay? So this is a general kind of representation of the elements. So the name of the element, the specific element X, say for example. Okay? Here we actually represent the mass number and here we actually represent the atomic number. Now, let me tell you one example here. Okay, board, here you have space, so I will write here. So we have, say for example, carbon, and it has a mass number of 12. It has a mass number of 12, and atomic number is 6. Okay, so please follow that. I hope you any element with its symbol is represented here. The mass number, I hope you remember mass number. Mass number is the number of protons and neutrons. And the atomic number is the number of protons. So, if you take this particular element, it is carbon, we have mass number 12, atomic number or proton number 6. Now, I hope you can understand that a very simple calculation here. Mass number is protons and neutrons. Atomic number, that is your protons. Now, when you want to calculate the number of neutrons, I hope it is very simple. That is mass number minus protons. I hope you are able to understand this. So mass number minus protons will be able to get the neutrons. So here it is 12 minus 6 is 6. So 6 is the neutrons number. So 6 is the neutrons number. I hope everybody is able to follow this, right? Please respond.
Yes, sir.
Yes, sir.
Alright. Okay. So, yeah. Did any student have any doubt? Alright. So, this is how a very simple representation goes with elements. So, this is especially for people from different background. So, a carbon atom with the mass number 12 and atomic or proton number 6, we actually get neutrons number by subtracting the mass number minus proton number. We'll be able to get the number of neutrons. Okay. Now this is one example. Now let me take one more example here. We will take another element. Say one example, nitrogen. We have the mass number 14 and atomic number 7. Mass number 14 and atomic number 7. Now, it is very easy to calculate the neutrons number. It is 14 minus 7, which is again 7. Okay. Now, these two are the examples. Now, the question is, are these two elements considered as isotopes? Please respond. Are these two elements considered as isotopes?
No, sir.
No. So, I hope you can understand from the definition. Why? Because atoms of the same element. So, you have to understand. Atoms of the same element. So, in the beginning itself, it is wrong. Here we have carbon, we have a different element here. So, atoms of the same element. So these two are not considered to be the isotopes of each other. And moreover, you have to follow the same number of protons but different number of neutrons. That is also not following here because the protons number is 6 and the protons number is 7 here. So that is also not followed. So these two are not isotopes of each other. So we can understand that. Now, let us go with another example. So I'll just write another example here. We'll take another carbon here, and we will have the mass number and atomic number 14 and 6.
Sir, your voice is not audible.
14 and 6. So now if you calculate the number of neutrons here, so it is mass number minus proton number, it is 14 minus 6.
The voice is not audible.
Huh?
The voice is not audible.
My voice is not audible, is it? Students, my voice is not audible? Other students, please reply.
We can hear, sir.
Yeah,
Yes, sir. I can hear.
you can hear, right? Other students, Jyoti,
Yes, sir, I can hear.
it is audible, right?
Yes, sir, it is.
Yeah, then the student who has a problem with the network issue, kindly check your network issue and see. Because for majority of the students, it is audible. Or else what I will do is I will just bring the table little front. Okay. I think there shouldn't be any problem now. So, you have to understand, these two are not isotopes of each other. But if you take these two correlates with this definition. How? Atoms of the same element. So, these two are same elements, carbon, with same number of protons. If you take, it is 6 and here also it is 6. So, they are same number of protons, but different number of neutrons. If you take this, the number of neutrons is 6, and if you take the number of neutrons is 8. So, we can tell that these two elements are isotopes of each other. So, these two elements are isotopes of each other. So, this carbon and with the mass number of 14 and 6, and this carbon with the mass number of 12 and 6 are good examples of isotopes. So, that is how you define isotopes. Atoms of the same element with same number of protons but different number of neutrons. So, that is the definition of isotopes, and this is how you represent the elements with their atomic and mass number respectively. Now, we will take another example. Another simple example we will take hydrogen. Now, if you take the neutrons number, it is 0. And here, it is 1. And here, if you take, it is 2. Correct? So now we can tell that all these three elements are isotopes of each other. All these three elements are isotopes of each other because atoms of the same element. So it is all hydrogen here. Same number of protons. The proton number is 1, 1, 1. But different number of neutrons. Different number of neutrons. If you take this is 0, this is 1, and this is 2. So these three are also isotopes of each other. So we have to understand this. So this is another example of isotopes. I think I'll have this. Okay. Now we are entering into the syllabus, that is radioisotopes. So, as I told you, without understanding about what is an atom, what are the composition of atom, what is an isotope, how do you represent an element, there is no point in directly jumping into radioisotopes. So that's why I just had a idea of the basics with radioisotopes. Now, speaking about this radioisotope, a very simple definition I can tell you. Atoms that contain unstable combination of protons and neutrons. Are called as radioisotopes. Okay, I repeat. Radioisotopes are those atoms that contain unstable combination of protons and neutrons. Now, you have to understand, it may be a little difficult to understand since we use the word unstable combination. Okay. I am just explaining an analogy, and after that we will come to radioisotopes. Okay. So for now we will forget about radioisotopes. I am telling you an analogy. Say for example, I am insisting Gopika to carry 2 books. Okay. So I am actually staying in 3rd floor. Gopika is actually staying in the ground floor. So I am insisting Gopika to carry 2 books with her, and I am asking her to bring it to me. I am staying in 3rd floor. So Gopika will be able to carry 2 books easily. So she is not supposed to use lift. So she's going to come through the steps. So she's going to use the staircase, and she actually crosses the 1st, 2nd, and 3rd floor. And finally, she carries her 2 books with her, and she reaches and gives the books to me. Now this is fine. In the second case, I am insisting Gopika to carry 10 books. Okay? I am insisting Gopika to carry 10 books on her hands. She is not supposed to use any bags. So simply she has to carry the 10 books with her hand, and she has to take it from the ground floor to the 3rd floor to me. And she is not supposed to use the lift. She has to use the staircase. Now, people can easily understand and guess that definitely she will end up in losing some books when she is going to come through. I can tell you, you can just imagine. So when she is actually coming through the 1st floor, she can lose 2 books. And again, when she is coming to the 2nd floor, she may again lose 3 books. And finally, when she is coming to the 3rd floor, she will be again having only 2 books. So this is one analogy which I want to tell you now. With Gopika, the stable combination of books is 2. You have to understand. The stable combination of books which she can bring from the ground floor to the 3rd floor is 2. But when we give her more burden of number of books, definitely she ends up in losing the books. And one more important point with this story, I want to tell you, the books are not actually lost one time. So I told you, in 1st floor she loses some books, in the 2nd floor she loses some books, and finally when she's coming to the 3rd floor also, she's losing some books, and again in 3rd floor she's having only 2 books. So the point which you have to understand from this narration is, the stable combination for Gopika carrying the books is 2. The unstable combination is more than 2. So if we give more than 2 books to Gopika to carry from ground floor to 3rd floor, she will definitely end up in losing. Similarly, if you have unstable combination of protons and neutrons, it is going to lose or emit or produce or release protons and neutrons. So that particular concept we call this radioisotopes. So this is an analogy. I hope you will be able to get a better idea about radioisotopes. And as I told you, very importantly, the protons or the neutrons are not released for one time. That is also very important. I told you she loses her books even in the first floor, even in the second floor, and even in the third floor as well. So it doesn't mean that it is going to happen only one time. So a kind of process which happens is unstable, again unstable, again unstable, and finally stable. You have to understand this. Okay? It doesn't mean that unstable actually directly reaches stable. No. Okay? It will lose its protons or neutrons until it reaches the stable combination. So without attaining stable combination, the elements will keep on losing its protons or neutrons. Okay? So that is a very important point which you have to understand as far as the radioisotopes is concerned. Okay? So that is actually radioisotopes definition. That is the atoms that contains unstable combination of protons and electrons. We call it as radioisotopes. And we also have another term, that is radioactive decay. So it is nothing much different from radioisotopes. Radioisotopes are the elements which actually releases protons and neutrons. And we call them as atoms that contains unstable combination of protons and neutrons. Radioactive decay is the process of an atom, okay, right? Radioactive decay is a process of an element's atom reaching a more stable state. Okay, is called as radioactive decay. So these two are not too much different from each other, and I hope you can understand. So radioisotopes is defined as the atoms that contains unstable combination of protons and neutrons. Radioactive decay is a process in which an element's atom reaching a more stable state by by losing or releasing protons or neutrons. So that process we call it as radioactive decay. Okay? So I hope you people are able to follow up with the things which we have discussed. We have just entered into the syllabus. Okay? So radioisotopes contains unstable combination of protons and neutrons. Since it is unstable, to attain a more stable state, it loses or it releases protons and neutrons. So that process we call it as radioactive decay. Okay. Now, the process of radioactive decay. The process of radioactive decay is of three types. So the process of radioactive decay is of three types. That is alpha decay. Beta radioactive decay is the second type of radioactive decay, and we have gamma radioactive decay. So these are the three different types of radioactive decay which we are going to study in detail. So alpha radioactive decay, beta radioactive decay, and gamma radioactive decay. Now moving on to the first type of radioactive decay. That is alpha radioactive decay. Okay. So we are going to discuss in a very simplified way that everybody can understand. Now speaking about the alpha radioactive decay, it involves emission of alpha particles. So alpha radioactive decay involves emission of alpha particles from the nucleus. From the nucleus of an atom. So from the nucleus of an atom, it involves emission of alpha particles. Now, what do you mean by alpha particle? We have to understand. An alpha particle contains two protons and two neutrons. An alpha particle contains two protons and two neutrons, and this, since it is identical to helium, we represent alpha particle as He, okay, 4 and 2. Correct? I am once again explaining. Alpha radioactive decay involves emission of alpha particles from the nucleus. Okay, I hope you know where the nucleus of an atom we have already discussed in the basics. So alpha radioactive decay involves emission of alpha particles from the nucleus. An alpha particle is going to contain two protons and two neutrons. If it is two protons and two neutrons, I hope you can understand the mass number is 4. 2 plus 2 is 4, right? Very simple. So the mass number is 4. The atomic number or the proton number is 2. Okay? So an alpha particle is going to contain two protons and two neutrons, which is identical to helium. So we represent alpha particle. So this is your alpha particle, which is represented by helium, mass number 4, atomic number 2. Okay. So let me write a general equation of alpha radioactive decay. Don't worry, equations are not tough. If you are able to understand, it is very easy. So feel comfortable in understanding the equations. We'll take X element A and Z. It is converted to a Y element A minus 4, Z minus 2 plus helium I'm sorry, A represents mass number, Z represents atomic or proton number. Now Y is A minus 4, Z minus 2. Why I have written A minus 4? Because the mass number of an alpha particle is 4. Okay, so that is A minus 4. And Y have written 2 minus 2, that is protons, atomic number. So plus this is your alpha particle. So this is your alpha particle. So this is the general equation of representing alpha radioactive decay. Now we will see a specific example of that. Ra, which is nothing but radium. Radium, it has the mass number of 226 and it has the atomic number of 88. So this is going to undergo alpha radioactive decay. So it is converted to radon. It is converted to radon. So I hope you can understand. It is 226 is the mass number. So here we will be getting 222. Why? Because 4 has to be subtracted, and here it should be 86. 86 plus helium, the same, 4 and 2. Correct? 4 is the mass number, 2 is the atomic number. Okay? So this is a very good example of alpha radioactive decay. Okay? So once again I am telling you, the radium, which is represented by the symbol Ra, has a mass number of 226, atomic number of 88, undergoes alpha radioactive decay. It is changed to radon with mass number of 222, atomic number of 86, and alpha particle helium, 4 mass number, 2 atomic number. So this is an example of alpha radioactive decay. Okay? Now, listen. Another important term which I want to tell you is, I'll write it here, transmutation. Now, very simple. This process is called as transmutation because previously it was radium, and because of alpha radioactive decay, it has been converted to radon. And because of that, it has been changed from one element to a different element. And that process we call it as transmutation. I repeat, it is previously radium and it has become as radon. Since it was previously one element and after undergoing alpha radioactive decay, it has changed to a different element. It is called as transmutation. Okay? Now, listen. I told you when I was speaking about radioactive decay itself that it is not going to attain its more stable state when the process is going to take place only one time. Remember the analogy. She'll be able to lose the books not only once, twice, thrice, and it keeps on going until she reaches the stable combination. A similar example you have to remember. Here we should understand that it undergoes further decay. Say for example this radon. So this radon has mass number of 222, atomic number of 86, undergoes further alpha radioactive decay to convert it into an element which is represented by the symbol PO, which is polonium. Polonium, and again what will be coming here? 218. Since there are 4 reduction, and here it will be 84. It will be 84 plus helium 4 and 2. Okay, so this radon is again undergoing alpha radioactive decay to be converted to polonium. Okay, represented by mass number of 280, atomic number of 84, and this polonium again undergoes alpha radioactive decay, and it is converted to lead. I hope you can calculate. 214, 82 plus helium 4 and 2. This polonium is again undergoing alpha radioactive decay, is converted to lead. This is lead. Pb stands for lead, and you have 4 in the reduction of mass number and 2 in the reduction of atomic number with the production of alpha particle. Okay, so this is also an example of transmutation. Why? Because radium is converted to radon, radon is converted to polonium, polonium is converted to lead. So since initially we have one element, and after alpha radioactive decay we have another element, we call the process as a transmutation. I think I'll stop it here. We'll discuss about the process of beta radioactive decay and gamma radioactive decay in the next class. If students have any clarifications, you can get it clarified with this 3 minutes of time. Once again, I am telling you, please listen properly to have better understanding of my classes. If you're not following me properly, then these equations and all the stuffs, it will be very tough for you to understand and face the examinations. So that's what I'm just explaining everything from the basics. We just started with atoms. We discussed about the structure of atom, the composition of atom, about isotopes, about radioisotopes, radioactive decay, and we went on discussing about this alpha radioactive decay. So in the next class, we'll be discussing in detail about the beta radioactive decay, gamma radioactive